Summer 1943. Across the endless skies of Europe, black dots bloom and vanish in flashes of white fire. Contrails twist, tracers burn red against blue, and B-17 fortresses scatter silver debris like metallic snow. The men inside those bombers have a single thought every second of the flight: who spots who first? For the U.S. Army Air Forces, now waging daylight bombing over the Reich, survival hinges on aim. Not just dropping bombs on bridges and ball-bearing factories, but hitting something infinitely faster and smaller: attacking fighters. The gunners have to win duels measured in fractions of a second between physics, instinct, and terror. In the cramped waist positions, machine guns chatter in staccato rhythm. Twin 50 caliber M2 Brownings spit out lead at 900 rounds per minute, chewed belts rattling around bare hands numbed by cold. Every tracer flashes once every fifth bullet, a brief signature to help guide the stream. But this visual guide is treacherous. Light travels faster than life, and perception itself lags behind motion. For months, defensive success in daylight raids remains dismal. German fighters, Bf-109s and Fbu-190s, slice through formations with frightening precision. They attack from high noon above or head-on, vanish through contrails, reappear astern before gunners can traverse. Each mission costs 50 bombers, sometimes 100. Every missed deflection means 10 men falling in flames. And the reason for so many misses is simple, but devastating. Pilots and gunners alike are aiming at where targets appear, not where they will be. The 7th Air Force Test School in Utah calls it chasing bullets. Gunners meticulously line tracers on the enemy, only to discover that their bullets, traveling 890 meters per second, take almost a full second to reach where the fighter used to be. In that second, a fighter at 400 miles per hour has already moved 170 meters. The sky becomes filled with perfect aim at an empty past. What American scientists and instructors realize through panic and math will change aerial warfare forever. To hit the future, you must aim at the future, not the target. The doctrine emerges from laboratories playing with chalkboard physics, relative motion, angular velocity, lead computation. But on airfields scattered from England to Algeria, theory alone feels absurdly abstract. Young gunners trust muscle more than mathematics. Until their first mission, each man believes the eyes defend him. Each comes home pale with the sight of tracers curving beautifully toward nothing. By late 1943, with losses approaching unsustainable levels, the Air Force formally establishes the Central Gunnery School at Tyndall Field, Florida. There, recruits learn what none of their instructors had fully grasped a year earlier: a concept so counterintuitive it demands men unlearn instinct itself. They call it the principle of deflection. Instead of chasing the aircraft in front of you, you fire into the space where it will arrive, factoring for its speed, angle, and your own motion. This is no trick. It is predictive geometry executed through nerves and reflex. For slow targets like ships or tanks, this is manageable, but for aircraft closing at combined speeds exceeding 700 miles per hour, a tenth of a second's misjudgment translates into meters of error. So why aim behind? Because aerial gunnery is not a single-plane equation. From a bomber's perspective, an attacking fighter seen at 2 o'clock high and diving across its nose is moving with enormous lateral velocity. Bullets must not only reach its future position, but meet its changing vector. Conventional wisdom says lead ahead, but engineers measure the aerodynamic lag of the bullets themselves, the slipstream deflection caused by the bomber's own airflow, and even the gravitational fall at high altitude. When all variables combine, the equations sometimes dictate a counterintuitive offset. Under certain attacks, the gunner must aim slightly behind the visible silhouette to intersect its true path. That adjustment seems insane, but the data doesn't lie. At Wright Field, Ohio, film cameras mounted to turrets record practice shoots using towed cloth targets called sleeves. Analysts freeze frames chronographically. The results show most effective hits cluster not on the nose of the silhouette, but a few aircraft lengths aft of it, because that apparent behind actually compensates for parallax, bullet drift, and the geometry of closing speed. Gunners who aim literally on the crossing point overshoot the target plane's line by yards. Those who aim fractionally behind shred the target. To spread this revelation through a worldwide army, instructors create something ingenious: The flex gun simulators. Inside dark huts lit by projection lamps, trainees rotate mock turrets guided by films of attacking fighters. Sensors calculate delay between trigger and image movement. Every new class returns staggering results. Once they internalize the idea of backward aiming and leading through anticipation, hit ratios double, sometimes triple. By autumn 1943, missions show it in real skies. Bomber groups that had lost one aircraft in 5 now lose one in 10. Casualties remain terrible, but survivability improves dramatically. Crews start murmuring a phrase that soon echoes across airfields. Don't chase them forward, pull back and let physics do the killing. The news spreads upward faster than command memos. Part 2 will dive into those physics, ballistic tables, airflow, relative motion, and the astonishing collaboration between scientists, mathematicians, and gunners that turned counterintuition into twice the accuracy mid-war. At its heart, aerial gunnery was a conversation between physics and fear. Every trigger pull began with hope and ended in invisible mathematics. The moment a .50 caliber round left the muzzle of a Browning, it entered a universe governed by scale and time alien to human reflexes. The bullet may have seemed instantaneous to the man firing it, but at combat ranges it was sluggish compared to the geometry unfolding around it. At 20,000 feet, air density dropped to half that of sea level. Each projectile lost roughly 400 feet per second in velocity before crossing a quarter mile. Spin stabilization kept trajectories straight for a fraction of a second before drag and gravity began to curve it downward nearly 20 inches every 100 yards. Meanwhile, both aircraft, the attacker and the defender, were rarely still. The bomber might be lumbering forward at 160 miles per hour, the enemy fighter diving at 380, shedding altitude like water off a cliff, changing its vector dozens of times before the gunner could index his sights. Trust instinct, and you would always miss. Instinct sees a straight line. Reality moves in arcs. The Air Force scientists at Tyndall and Wright Field learned quickly that human brains could not compute this in real time with pure thought. They decided to teach through pattern memorization. The new doctrine divided attacks into zones defined by angle and closing speed. The manuals displayed silhouettes of German fighters with color bands indicating how much lead or lag to apply when firing. At certain attack angles, most famously a 60-degree diving sweep, the mathematically correct deflection lay not ahead but fractionally behind the enemy's tailplane. Aiming there allowed bullets, falling through parallax distortion, to enter the target's wing route. Early tests felt like heresy to pilots who had grown up with hunting rifles. Then the data arrived. Tyndall's range officers began recording results frame by frame on 16mm film using a strobe synchronized to bullet trails coated with magnesium tracer. Each exposure froze a line of fire like a chalk mark through the sky. When these trajectories were compared to the moving drone's paths, it became clear why so many bomber gunners missed. They followed line of sight. The bullet's true flight was warped by aerodynamics, drag, and relative rotation of the bomber's firing platform. In simplified terms, the bomber itself acted as a moving gun carrier whose speed affected the bullet even after it left the muzzle. A projectile fired rearward from a Fortress's tail turret inherited the bomber's 160 miles per hour forward velocity, subtracted from its 2,900 FPS muzzle energy, altering its arc throughout flight. Depending on wind and slipstream contours, some arcs bent left, others right. Firing behind no longer meant cowardice. It meant adjusting for a machine's invisible hand. To teach this counterintuitive logic, the U.S. Army Air Forces built technological marvels that bordered on science fiction for their time. One was the Waller Gunnery Trainer, a massive projection theater with dual optical projectors linked mechanically to real gun handles. On a curved screen, filmed fighters dove and rolled as sensors tracked angle and time delay between trigger and image intersection. Each student's scorecard printed hits and misses automatically through a set of phototubes, recording light flashes across the target frames. The key discovery from months of training analysis was psychological. Accuracy improved when gunners stopped consciously estimating distance and simply trusted learned deflection patterns, feeling when to press the trigger rather than aligning crosshairs in panic. Instructors called it programming the reflex. They repeated a mantra identical to that of baseball coaches: don't aim at where it is, throw to where it's going. But for aerial war, where it's going was a cube of space calculated in vectors and seconds. That cube existed invisibly within imagination. Mastering it demanded forgetting natural reactions shaped by gravity-bound life. For combat veterans returning to retrain new recruits, this doctrine reinvented the very language of survival. Staff Sergeant Dwight Harlan, one of the earliest graduates, described it vividly in his letters. They told us to shoot at ghosts. You pull the trigger, seeing nothing in the sight, only empty air, and a moment later, that air explodes into aluminum. By late 1943, operational squadrons in England, especially the 91st Bomb Group based at Bassingbourn, adopted the new methods wholesale. Gun cameras installed in their B-17 turrets provided empirical proof. Frame count analysis from November missions showed a 110% increase in recorded strikes against attacking fighters, particularly those making head-on passes. The same gunners trained under old doctrine averaged roughly 1 hit per 200 rounds. After reschooling, results improved to 1 per 90. The effect multiplied across hundreds of aircraft. But technology continued to refine the idea. One challenge remained unsolved: the limitations of human reaction time. Even with perfect knowledge, men still took a quarter second to register visuals and squeeze triggers. At airspeeds exceeding 400 miles per hour, that delay could push every pattern of fire yards behind. The answer emerged unexpectedly from British radar research: the creation of analog computing gun sights that could translate movement into prediction. In early 1944, American engineers visiting RAF Boscombe Down observed tests of the MCAC-2 gyro gun sight. Inside its housing spun gyroscopes that deflected mirrored reticles as the pilot or gunner pulled the handle in proportion to turn rate. The moving sight automatically projected where bullets would intersect. American ordnance experts collaborated to recreate and ruggedize the device as the K-14 optical gun sight, soon standard on P-51 Mustangs and select bomber turrets. Adjusting a dial for target wingspan and keeping the enemy framed centered gave automatic compensating lead, doing with mechanics what tinlers had been beating into muscle memory for 2 years. For heavy bomber crews still firing manually, the human brain remained the analog computer. They learned to visualize enemy angles as slices of a clock: 12 o'clock high, 3 o'clock level, 6 o'clock low. Charts pinned inside turrets translated each reference into inches of offset and seconds of burst. An attacking FD-190 closing from 2 o'clock high at 400 miles per hour required the gunner to begin firing when it was still 2 aircraft lengths short of the gun sight cross, then hold continuous fire into apparent emptiness. For the first dozen missions, this felt unnatural cruelty to instinct. Yet slowly, statistics grew incontrovertible. Early Allied raid data from Schweinfurt-Regensburg in 1943 showed a kill ratio of 2.1% per fighter engagement. By mid-1944, after adoption of corrected deflection tables and psychological conditioning, the figure nearly doubled to 4%. In the sterile mathematics of war, that simple geometric insight meant survival of entire bomber crews, and multiplied by hundreds of raids, the survival of the daylight bombing strategy itself. Still, teaching men to trust computation over panic required more than engineering. It demanded faith. Combat footage circulated in intelligence theaters across the Air Forces, film reels titled Through a Gunner's Eyes. They were both propaganda and instruction. The narrator's calm voice over tracer-lit skies repeated the creed: "He's not there anymore. Aim where he will be, shoot the future." The idea reached beyond laboratories. Fighter pilots returning from escort missions reported adopting similar adjustments, not behind in space, but behind in time, timing bursts a split-second earlier or later depending on converging trajectories. The entire air war was beginning to operate as predictive chess. But prediction, unlike instinct, has limits. Every calculation grows uncertain amid adrenaline, flak bursts, and spinning aircraft. The final breakthrough would come from translating those invisible equations into tools that removed human doubt, a partnership between physicists, ordnance officers, and frontline crews that would turn deflection theory into automatic systems. By spring 1944, the air above Europe had turned into an equation written in vapor and gunfire. The strategy of aiming behind the target was no longer just a training quirk whispered among gunnery instructors. It had matured into a codified science, a doctrine that blended physics with instinct and turned survival into mathematics. But mathematics demanded instruments equal to its logic, and human reflexes were reaching their limits. The new enemy wasn't merely the Luftwaffe, it was time itself. Between a gunner seeing a fighter and pulling the trigger, 250 milliseconds vanished, the blink of an eye. By the time the first bullet left its barrel, a diving Messerschmitt had already shifted 30 meters in space. To compensate, the U.S. Army Air Forces began merging man and machine through mechanical computation, an engineering revolution hidden inside rotating glass domes and gyroscopic cages. The principle was brutally simple, yet technologically miraculous. If a gunner couldn't correct fast enough, the gun had to do it for him. Inside the K-13 and later K-14 gyroscopic gun sights, engineers used spinning gyros linked to a system of optical prisms and mechanical cams. As the gun barrel moved, these gyros sensed angular acceleration relative to gravity and projected a moving dot, the predicted point of impact, onto the gun sight. The further the gun swung to track an enemy, the further ahead or behind the dot slid, automatically compensating for lead, lag, and bullet drop. For pilots in P-51 Mustangs and gunners in B-17 turrets alike, the effect was alchemy. Instead of hunting with guesswork, they chased a tiny, glowing prediction of the future, a mathematical ghost hovering on glass. To understand its importance, we must step momentarily into the inner mechanics of air combat fire control. At the heart of each Browning M2 lay a precise tempo, 850 to 900 rounds per minute, translating to one bullet every 0.66 seconds. Even at 2,900 feet per second muzzle velocity, that bullet required nearly a second to cross 1,000 yards. During that second, an attacking FW-190A8, banking at 380 miles per hour, changed position more than 550 feet. The pilot who aimed directly at its nose tore empty air. The gunner who compensated by reflex might guess right once in 100 tries. The gun sight, however, never guessed, it measured. The installation of gyro sights across American and British Air Forces transformed battlefield arithmetic. Flight test records from Wright Field's armament section reported hit probabilities rising another 80% after adoption, even among novice crews. Training commands called it revolution by gyro. To every gunner, it felt like clairvoyance. Aim apparently behind, squeeze, and a second later see the falling streak of a burning attacker crossing exactly where the dot had been. Physics had become prophecy. Still, the K-14 was not the end, merely the most visible proof of the theory at work. Engineers understood that deflection wasn't merely horizontal. At altitude, air density changed drag. At oblique angles, relative wind from the bomber's slipstream curved bullets along parabolic arcs. Analysts created charts integrating not just forward or rearward lead, but vertical range compensation. Gunners learned to fire slightly over descending targets to let gravity drop rounds into their paths. Behind every trigger pull stood entire laboratories. Norton bomb sight engineers repurposed analog computing systems from bombing to gunnery. MIT's radiation laboratory ran experiments with electromechanical predictors that read target motions off radar echoes. In England, the Royal Aircraft Establishment at Farnborough mounted film cameras on gun turrets and plotted tracers frame by frame across translucent overlays, data that refined both American and British manuals. Inside the massive AAF Gunnery Research School at Laredo, Texas, instructors correlated thousands of gunnery sessions. They measured delay between trigger and hit, recording average angular errors per attack type. Statistically, most fatal mistakes came not from bad eyesight, but from wrong timing, underestimating how much the enemy's speed changed the geometry of engagement. In the dense vocabulary of the reports, one phrase appears repeatedly: -16 milliradian correction, aim behind trailing edge. Translated into plain terms, that meant pulling guns a fraction backward into what the eyes insisted was failure. Yet every film strip proved it. When bursts began just aft of the wing root, impacts converged on the cockpit. A half degree of humility beat a lifetime of instinct. In combat, the shift became cultural. Stainless steel placards appeared in bomber turrets stamped with a single reminder: don't chase the trace. Waist gunners wiped the frost from those letters before every mission. Even new recruits whispered it as a prayer. They had all seen the original sin of air war, littering the sky with rounds curving harmlessly through vacated airspace. On February 20th, 1944, the first day of Big Week, the bombing offensive that shattered German aircraft production, the impact of the new doctrine became measurable. More than 1,000 bombers crossed into Germany. The Luftwaffe responded with ferocity, 750 fighters clawing upward through contrails. Interception reports later tallied results inconceivable just 6 months before. American gunners claimed 262 victories for 21 plane losses, a ratio no longer explained by luck or miscounted boasts. Forensic analysis of wrecked German aircraft confirmed the data. Hundreds carried impact patterns grouped exactly along predicted intercept angles, wings and tails chewed out by gunfire originating from defensive positions no human instinct alone could have calculated. Journalists visiting airfields after the mission were astonished by the gunners' calm, almost clinical tone. Staff Sergeant Hal Sampson of the 447th Bomb Group summarized it, "They told us to shoot wrong, so we started hitting everything." The irony was poetic. By late spring, training films and booklets formalized what every experienced crewman now knew by touch. The newest manuals, AAF Manual 2010 Deflection Firing Techniques, outlined both forward and reverse aiming offsets, depending on crossing angle, airspeed, and closure rate. For each category, Ballistic Solutions recommended incremental adjustments measured in degrees of lag. Once incomprehensible, those charts became scripture memorized by thousands, but improvement never ended. Mathematicians sought to automate even these tables. Buried in paperwork and schematics at Wright Field's Project D division lay one experiment decades ahead of its time, an analog fire control computer combining gyros, potentiometers, and vacuum tubes. Through it, the bomber's own radar measured the angular velocity of incoming targets and translated correction directly to turret motors, preceding the target by exact infinitesimal margins. The technology failed to mature before war's end, but predicted what the Cold War would eventually perfect: radar-directed, servo-controlled automatic turrets. On the front lines, the evolving doctrine changed more than kill ratios, it reshaped morale. Crews who once stared through plexiglass canopies, helpless and reactive, now possessed knowledge powerful enough to calm fear. Survival became not guesswork, but science, and science could be trusted. Even so, the new precision carried its psychological weight. Veterans admitted later that the eerie confidence of aiming wrong to be right lingered long after the war. The act itself forced them to separate instinct from proof, emotion from calculation. They had learned to see chaos as a system, and that lesson, they realized, applied beyond combat. "Once you know to fire into emptiness and still hit," one gunner said after the war, "you stop doubting anything mathematics tells you." And mathematics continued to evolve. Theories born in the tight metal bubbles of bomber turrets soon fed the design of early missiles and radar-guided guns. Engineers who had once drawn deflection tables now worked at Bell Labs and Northrop, applying the same predictive formulas to servo circuits and flight computers. Aiming behind the target in the 1940s would become the ancestor of proportional navigation in the 1950s, the algorithm that guides every modern missile today. But in 1944, all that mattered was that the skies, once ruled by the interceptor, had tilted toward the defenders. The ratio of loss between bomber and fighter, once catastrophic, had fallen by more than half. Escort fighters and better coordination played their roles, but inside every formation, gunners knew their part. The moment they aimed against instinct, they had wrested chaos into predictability. By summer, American photographers documenting air victories noticed a subtle shift on returning crews. Gun barrels still smoked, but faces no longer showed disbelief. They had expected to hit now. Engineering had become faith, and faith measurable. When peace finally came in 1945, the men who had fired into empty air and watched enemy planes dissolve within it returned home to a quieter world. Yet for the scientists, engineers, and tacticians who had taught them to aim behind their targets, the war's end was not an epilogue. It was the beginning of a new era of understanding. The revolution they had started in those vibrating gun turrets had rewritten the logic of pursuit and prediction itself. The invisible principle born in the sky, lead, lag, and the unyielding flow of time, would soon define not only combat, but technology. Everything from radar interception to guided missiles and even future spaceflight would trace its lineage to that discovery, that you must act not on what you see, but on what will be. Post-war legacy, turning practice into principle. Immediately after the war, the U.S. Army Air Forces began compiling data from the thousands of gun camera reels and debriefing logs collected between 1943 and 1945. Historians studying this avalanche of statistics realized they weren't just recording history, they were documenting a transition point in scientific thought. The project's analysts at Wright Field called it predictive engagement theory. In their combined 14-volume report, they summarized the miracle of deflection in one sentence. Effective fire is not reaction, but anticipation quantified. For the first time, mathematicians worked closely with psychologists to unravel how the human brain adapted to complex spatial calculations while under mortal stress. Researchers armed veterans with small analog replicators, measuring reaction time and procedural learning. Many discovered that prolonged exposure to predictive firing had rewired reflexes. Muscle memory had fused with a subconscious model of relative motion. These men quite literally thought in vectors. This insight birthed the first wave of post-war flight and missile mathematics. Dr. William B. McLean, a physicist formerly with the Navy's Bureau of Ordnance, took those same calculations of lead and lag and poured them into a set of feedback equations that later powered the guidance system of the AIM-9 Sidewinder missile. What a gunner had done instinctively in an open turret, McLean taught a machine to do electromagnetically. Every modern heat-seeking or radar-guided missile still follows the same principle: a continuous, proportional correction behind the target's current location to intersect its future one. If a bullet in 1943 required brain and luck, a missile in 1953 demanded memory and logic, both descendants of those silent lessons over Germany. The rise of predictive control. While ordnance laboratories evolved those formulas mechanically, the theory also crossed into a surprising arena: computing. Young physicists returning from wartime ballistics teams migrated to institutions like MIT and Caltech, carrying experience with analog fire control computers. Their work inspired early digital systems devoted to feedback correction. One of these post-war students, Norbert Wiener, published Cybernetics in 1948, describing the same feedback loops and predictive control the air gunners had practiced instinctively. In interviews, Wiener credited the study of anti-aircraft predictors as his awakening to the power of self-adjusting systems. Thus, the seemingly narrow act of correcting gunfire evolved into a mathematical movement influencing automation, robotics, and even modern software algorithms, all grounded in anticipating movement before it occurs. Human lessons among machines. For the men who had survived those airborne furnaces, the transformation felt painfully human. Many described a lingering unease. After learning to trust mathematics over instinct, daily life seemed both safer and stranger. Former turret gunner Lou Morrison told an interviewer in 1950, "Ordinary driving feels too slow. When I see another car turning, my brain still fills in its future path, not its present one." Others carried the same paradoxical calm that had saved them in combat, acting against panic, believing in something they could not immediately see. Aiming behind a target had become philosophy, the discipline of patience, of detached anticipation in a chaotic world. The technology that never slept back in laboratories, the obsession with precision never stopped. Engineers miniaturized gyros, refined optics, and introduced electromechanical analog circuitry capable of predicting target vectors 10 times faster than any human operator. By the early 1950s, Bell Labs and General Electric were producing fully automatic fire control directors for naval guns. These descendants of the K-14 system derived directly from the wartime gunnery equations. When radar tracked an incoming aircraft, computers calculated intercept points automatically. The operator simply authorized firing. No trigger rhythm, no guesswork, just pure predictive engagement. The effectiveness of these systems stunned naval historians. During Korea, American ships equipped with the Mark 37 radar director recorded hit percentages against aircraft equal to or greater than those achieved by experienced WWII fighters. Human vision had been replaced by data. In this sense, aiming behind the target symbolized humankind's first step into predictive automation, machines not reacting but foreseeing, the numbers behind victory. Statistically, the shift could be measured in the most unforgiving of currencies, survival rates. In early 1943, before revised doctrine, U.S. bomber forces averaged one enemy destroyed for every 5,000 rounds fired. By late 1944, after introduction of advanced gunnery techniques and gyrosights, that number had fallen to one victory per 2,000 rounds. The difference sounds minor until scaled by industrial war. Across the 2.7 billion 50-caliber cartridges fired during the European campaign, that efficiency saved thousands of lives and hundreds of aircraft. Behind those statistics lay individual victories often recorded in seconds and fractions. Gun cameras from the 303rd Bomb Group show long bursts that once traced aimless spirals, now arching cleanly into convergences of sparks, tearing across FW-190 wings. Every frame is a line graph of comprehension, catching up to catastrophe, a revolution in mindset. What separated 1945 from 1942 was more profound than a piece of hardware. Soldiers had learned to surrender instinct to intellect without losing courage, to place faith in abstraction. It was this reversal of belief that defined the technical century to come. When the jet age arrived, its pilots, too, relied on artificial horizons and radar displays, unseen equations translating motion into trust. Every autopilot, every ballistic computer, every guided bomb derived logic from that uncomfortable truth discovered in those vibrating gun tubs. The eye lies, the math does not. Training centers after the war preserved the memory deliberately. At Wright Field, later Edwards AFB, where experimental aircraft now broke sound barriers, instructors still showed wartime reels of B-17 gun camera hits. The moral was written not across explosions, but across equations. Beneath the film reels, opening credit appeared a motto that would resurface later in NASA briefings and Cold War control rooms. Anticipate, don't react. Echoes in modern warfare. By the 1960s, the very same predictive algorithms that allowed bomber gunners to double their accuracy had been reborn inside the guidance computers of early surface-to-air missile systems, from the U.S. Nike to the Soviet SA-2. Their radar circuits performed continuously what the wartime gunner once did manually: calculate the closing vector, predict the future position, and steer toward an invisible solution 3 seconds ahead. Modern electronic warfare, too, owes its existence to that moment of revelation. Signal tracking jammers and interception software use the same geometry of anticipation, deliberately aiming behind or offsetting frequencies to intercept transmissions that will not arrive for milliseconds. Physicists call this methodology retrodiction, calculating backward from expected futures. Philosophers call it foresight. Airmen simply called it survival. Personal reflection, aiming into the future. When interviewed decades after the war, many surviving gunners spoke of a peculiar anxiety the doctrine had left with them. Sergeant Hal Sampson summed it best. War teaches you to think ahead of what you can see. I left the service and realized that's all life really is, leading the target before it passes you by. They had become veterans not just of combat, but of perception itself, living proof that truth sometimes exists 1 second ahead. The same men who once misfired through instinct now wrote engineering textbooks, taught physics, built avionics industries, and helped design systems that would later guide spacecraft to the moon. When Apollo 11's landing computer calculated descent paths onto the Sea of Tranquility, it used the same kind of predictive algorithm, integrating position, velocity, and acceleration into future intersection points that had once guided 20-year-old gunners through smoke and terror over Berlin. Coda, the equation of faith. From the outside, history remembers the WWII air war for its heroism, dogfights, and hardware. But beneath every photograph of tracer fire arcing through clouds lies an invisible shift. Humanity learning, for the first time, to trust the predictive over the present. That shift changed warfare, then engineering, and finally culture itself. It defined a species no longer content to react, one that calculated forward, from firearms to spacecraft, from cockpit to computer chip. So when veterans spoke of aiming behind the target, they were describing more than ballistics. They were naming the moment the modern world began thinking in time's third dimension. The bullet that left a Browning in 1943 was more than a round of metal and cordite. It carried within it a seed of philosophy, that success depends not on where you are, nor even on what you see, but on how far ahead you dare to imagine. And in that flash between trigger and impact, as tracer arcs converged perfectly on enemy wings, history itself learned the truth those young men discovered in smoke and flame. You win not by chasing what exists, but by hitting what has not yet arrived. The silence that followed was not peace, only the echo of mathematics reaching its mark.